a circuit of a power oscillator working in the shortwave band from, say, approximately 7.6 megacycles up to 15 megacycles, and the whole circuit is here. I had to make it in this way because I wanted to mount it in this box, and in general I don't like to make my circuits in this way on this type of board, perf board, but here it is, like I made it, with some components on the back side and many components on the front. The circuit is here. It's a kind of multi-vibrator circuit, though I'm not absolutely sure, because we have here a coil, so that coil is driven in and out in a sine wave way with the help of these two transistors. And I've used by purpose a BD139 that has a good, say, frequency range, goes even up to high F frequencies. And here is the coil. It was made here, 6 windings and another 6 windings, and here on the central tap we send in the voltage of the power supply, and it can be between 4 and 12 volts. A 10 nanofarad bridges the positive and the negative lead, and furthermore there's not so much more to tell. It's a kind of classical oscillator circuit, a balance, so-called balance circuit, balance oscillator. And from the collector to the base we have this combination, a resistor and a capacitor, and also here from the collector back to the base, so that the whole circuit starts to oscillate. Here is the ferrite rod, 8 millimeters in diameter, length 3 centimeters. You cannot see that very properly here because I've used tape, etc, etc. So anyway, this is the way to make that coil. And there's also in that coil an antenna winding, so here you can say connect an antenna. In the ideal way it has to match exactly with the frequency that's generated in the circuit. Anyway, wire that I used, and here how it was made. Well, only an idea to make it this way. You can make it in many other ways, and the circuit has its good property that it more or less always starts to oscillate due to the, say, balance circuit and the kind of multi-vibrator setup. We look now on the scope to the frequency that's generated, and it's generated on 7.85 megahertz. That's very good. Of course, I will switch. Oh, that's not good. Wanted to switch off the lights, but the scope was also connected, sorry, to the same voltage. Anyway, perhaps this will help to get a better view on the waveform of the scope. Okay, let's go on. 7.8 megahertz, quite good waveform, and I give now more amplification to the scope, and let's see what happens when we take out the ferrite rod here, that will of course have an effect on the frequency, completely to the electronics theory. We are working on 7.9 volts at the moment. So I take out the ferrite rod now and let's see what happens. Waveform dances somewhat. Now gets a little bit stable and we are on 15.3 megahertz. Take it out completely and we are on 16.6 megahertz. I will try to stick it in. I hope that will succeed with one hand. And now I stick it in completely. Of course we see the frequency change. Now we are on 7.7 megahertz. And I tell it's a power oscillator, and that has everything to do with, in a certain way, of course, the voltage that we send to that oscillator, but also on the frequency. And I will take out now that ferrite rod and see where the whole circuit starts to take kind of substantial current. That's of course important when we are talking about a power oscillator. So I will take out now and push in that ferrite rod and let's look at the current. And we go now to the voltage where it is made for, that's 9 volts. And you can see already on the meter here that current is taken, and I stick in the rod now and I take it out, and you can see on the meter, on the amperemeter, where the ideal frequency is, where this power oscillator takes a lot of current, and that's here 200 milliampere, and the transistors here, BD139, really get hot. So, and we have this waveform. That's perhaps important to show. It's in a kind of way no longer a sine wave, but a kind of pulsed wave. That's strange, of course. Not a sine wave, but a pulse wave. That can, the reason for that can be everything. The biasing of the transistors, the reason that I've mounted here my scope to the antenna coil of this circuit. So here, this part could also have an effect on the waveform. So the antenna is not able to stray freely out its energy into the atmosphere. Anyway, well, perhaps the heat development, etc., and of course also the way that these both transistors are driving each other. When you change the values here, other resistors, other capacitor value, etc., perhaps this will show another waveform. This will produce another waveform. Has everything to do with the electronics and radio theory. Anyway, it's an interesting circuit to do experiment with. Now we'll take the coil completely out now. We have here, say, a good sine wave. Say, not very bad, but not perfect, but anyway. And at the same time we see that the current has dropped to a very low value, etc. So when you want to use this circuit, there are many things to be taken in account. The antenna length, the frequency where it works, depending on the windings, and the property of the ferrite rod, the ferrite core of the coil. Of course, the 100 picofarad capacitor plays a role. When you make it smaller, say 20 picofarad or so, the whole circuit will go to higher frequencies. Anyway, interesting thing, interesting circuit to do experiments. And it always works. That's important.